recording. Okay. All right. Good work, but we'll move on here now. All right, let me get this off here. Kramer's rule. All right, Kramer's rule. What is Kramer's rule? Okay. Wasn't there a, is it Seinfeld? It used to have somebody named Kramer in it. Has anybody heard of that Seinfeld show? Maybe, I don't know, this may be before your time, but okay, great show, Justin. So is there a guy named Kramer on that show, Justin? Is there, okay, all right. I heard he's kind of crazy, right? But now this is a different Kramer here. This is a different Kramer that we're talking about here. All right, you have learned you've learned 3 ways actually to solve a system of equations. One is you can do regular row operations. If the system of equations involves a square matrix, you could solve the system, your solution of vector x by doing A inverse times B. And then you also learn about LU factorization. Okay, so you've seen multiple ways to solve systems of equations, and here's another one called Kramer's rule. So Kramer's rule, it's needed in a variety of theoretical calculations. Okay, so it can be used to study how the solution of AX equals B is affected by the changes in the entries of the vector B. Okay, so the rule is given here. Whoops, hold on. Oh wait, they do mention one thing. We're going to look at the proof of this rule, but this matrix A sub I of vector B, that's defined as the matrix that has the columns of the matrix A, except you replace the ith column with the vector B. So think about taking the matrix A, okay, leaving it as it is, except you replace the ith column of the matrix A with the vector B. That's how A sub I vector B is defined. And in the rule here, you can solve for your variables. You can solve for your variables by taking the determinant. And by the way, this is for A has to be a square matrix, okay? Has to be a square matrix. So you have to have a system A, X equals B, where A is a square matrix. So you can solve for your variables, x1, x2, x3 up to xn, by simply finding the determinant of A sub I of the vector B and divide it by the determinant of the matrix A. And that's why A has to be invertible, because if the A is not invertible, then the determinant of A equals 0, and you wouldn't have a defined solution. So this Kramer's rule, it's nice because you see, if you were to just vary the vector, you could easily program this in the computer. And if you just change the vector B slightly, it'll change the numerator, the determinant of A sub I of vector B, and it can be used for theoretical computations. So the proof is not hard of this Kramer's rule. The proof is not hard. They outline it here in the book. One moment. So if you denote the columns of your matrix A by those vectors A1 to AN, and then the columns of the identity matrix by the vectors E1 to EN, then AX equals B. If AX equals B, The definition of matrix multiplication shows what you see here. So let me now just highlight this part. Let me see, can I paint that? Or okay. So let's say that you have the identity matrix, but it's not the identity, it's the identity where you replace the ith column with the vector x. And we're just going to decide to multiply A times that I sub I of vector x matrix. Well, by matrix multiplication, you take A and multiply it by each column of that second matrix. And that's going to give you then, that's going to give you the matrix whose columns are these columns here. But in fact, if you take the matrix A and multiply it by the E1 vector, you would just get back, let me just sort of, A times E1 is, hold on here, A times E1 would just equal A1. A times E sub n would just equal A sub n. It would be the last column of the matrix A. And A times X, of course, by definition, is equal to B. So in fact, this is just the definition of A sub I of B. So you can take the matrix A and multiply it by this special matrix I as defined here. Well, as you know how it's defined. It's defined, you know, that way. And you'll get A sub IB. And what you can do is you can then take the determinant. And let me see here. Let me just kind of, I like to kind of highlight things appropriately. Only takes a minute to do. Please tell me the book's showing. Good, good. So if you consider then that A times that special matrix I is equal to this A times I of B, then you can take the determinant of both sides of that matrix equation. And the determinant, the determinant of the product on the left is the product of the determinants. But the second determinant on the left is simply equal to X sub I. Okay, that's what it would equal. Because, well, let me see here. One moment. Hold on. Let me see if I can convince you why that's true. Hold on. Let me show you on the whiteboard. Let me go to the whiteboard and show you that. Okay, so if you had, you know, if you had like 1, 0, 0, and x1, x2, and x3, and then 0, 0, 1, this would equal I sub 2 of the vector x. So what you're doing is you're taking the identity matrix, you're leaving the first column alone and the third column alone, but the second column of the identity matrix, you're replacing it with the vector x. So the determinant of this matrix Well, why don't we expand along the first column? Okay, cofactor expansion on the first column would be plus 1 times the determinant of this matrix, right? Of that submatrix, which you know well, doing your cofactor expansions from section 1.1. And that's just going to equal 1 times, well, okay, x2 times 1 minus x3 times 0. And this just equals x2. Yeah. So is everybody okay with that result? The reason I'm showing it to you is that in proving Cramer's theorem, it's a step that it's mentioned, but not really proven. And I just wanted you to show it. I just wanted to show it to you. So in general, the determinant of this matrix is equal to x sub I. And we showed it for this little example here. We showed it for this matrix, but if you know, believe me, it's true all the time. So let's go back to the proof then. Are there any questions on this? All right, let's go back to the proof. And so now, when they say the second determinant on the left is simply equal to x sub I, now I think we're comfortable with that. And so, therefore, the determinant of A, let's see what that little, oh, cool, I can do, hey, I can do it kind of piece by piece. Now we're talking. The determinant of A times xi equals the determinant of A sub I of B, and so x sub I is the quotient of the determinant of A sub I B over the determinant of A. It's that simple. Okay, that's simple. So applying Cramer's rule, I guess it's really pronounced Cramer's rule. Applying the rule to solve the system is very simple. Here's an example. Okay, there's an example. And you view the system as AX equals B in example 1. You know, you have to identify your matrices A sub 1B, and A sub 2B, and they do. Okay, are there any questions on that at all? Well, and then you just compute the determinant. X sub 1 will be 20, and you just you just do the computations. It's really just a computational thing. Okay, and for the homework, your matrices using Cramer's rule will not be larger than a 3 by 3 because you know, computing the determinant does take time, for a little time for the 3 by 3. But of course, hopefully you'll use the row operations right? To help you, the properties of determinants with the row operations, that those can be very helpful. Okay, and they have an example in below. Here, let me make sure we're okay. We're good. They have an example below where they talk about applications of engineering. How many have heard of Laplace transforms? How many maybe have seen those in differential equations? Okay, so we have a few students that have. Very good. Benjamin, Marvelous, and Justin. And so the example below illustrates an algebraic system that may arise. And so I don't want to go into heavy detail on this, but they want you, given this system, they want you to determine the values of S for which the system has a unique solution. And so what they do, hold on. What they do is they apply Cramer's rule to compute x1, to compute x1 and x2. And then based on the right-hand side, okay, based on the denominators, okay, the system has a solution if S isn't equal to plus or minus 2. Okay, you can't have a 0 in the denominator. Okay, so it's just an analytical problem that example 2 is about. Are there any questions on that? All right, well then let's move forward here. Let's move forward in the book. So let me keep going forward here. So right now, I'm going to focus on other things in the section. So one thing that comes up is determinants as areas or volumes. How many maybe know that a determinant can be interpreted as a volume of a of an area of a parallelogram? How many maybe have heard that? I'm not sure how common. Okay, Lewis, and where have you all, Lewis and Eleanor, and oh wow, okay, and where have you all seen this in another class? Like, okay, okay, Eleanor was in the homework. Okay, and I know there was a problem at the end there dealing with that. So I wanted you to kind of be prepared. But have any of you seen that in another class? Like maybe multivariable calculus, or I'm just curious. Okay, Hung's recalls it from multi. Okay, all right, good. So I mean, you know, this can be, determinants of a 2x2 can be interpreted as a 2x2 matrix where the columns of the matrix A are vectors that define the parallelogram. You can find the area of that parallelogram by computing the determinant of A while taking the absolute value of it. But for a 3x3 matrix, you can have volume of a parallelepiped. And this idea can even be extended. They go on a little later in the section here, and they talk about actually using linear, if you have a linear transformation from one space to another space, and you want to find the, S is a parallelogram, and you want to find the area of your transformed parallelogram, there's a formula for that as well. and even it gets extended to volume of a transformation of a parallelepiped. I mean, it's really absolutely fabulous result. You don't see it, and they prove it below. It's not that really that hard to prove, but these are results that I think you should be aware of, because they could come up in like multivariable. A few students have already seen, determinants as areas and volumes. So I think it's good to be aware of it. And this might come up in a more theoretical class, but it's really a fascinating result. So what I want to do here, on that note, let me just try to help you appreciate this theorem 9 in the book. So as an example, I want to prove theorem 9. I want to just prove it. It's not that hard. So theorem 9 in section 3.3. Let me give you a moment to copy this down. We're not going to prove the entire theorem, just the part where about the determinant of a 2x2 matrix A being the area of a parallelogram. Okay, so let me show you how I actually prove this. I'm just double checking one thing. All right. So what I do is this. Okay. I'm gonna maybe put this in. I mean, it's a proof, but it's sort of it's essentially it's an intuitive proof. But I think they're very valuable. So what I do here is I draw a picture of a rectangle. And the rectangle is, how's this rectangle defined? Well, there's a vector here given by A0, and there's another vector here whose components are 0b, or yeah, I want to be careful how I phrase that, but that's okay. So this here, right here, is the coordinate say A, zero. So I drew the vector A0 there. And this coordinate here, it's on the y-axis. This is the y-axis. This coordinate here is 0b. And it's a rectangle. And I think you agree the area of that rectangle would be A times B. So now let's look at the determinant whose columns are A0, that's this vector here, and 0b, that's this vector here. And I think you agree, those two vectors define the rectangle with those vectors as sides. Well, the determinant of this matrix here is just A times B. So certainly, if you have a rectangle, if you define your matrix by using the side vectors of the rectangle as the columns of the matrix, the determinant of that matrix would equal the area of the rectangle. Is this reasonable? What I mean, up to here, is this reasonable? What I've written there? All right, Benjamin's comfortable. Okay, one moment here. Okay, so this is your this is your matrix A here. All right. All right. Thank you, Lewis. All right. Well, let's go to the next picture. Now, the next picture is where I've drawn a parallelogram, and the one side we're still coming out, from the origin. We're still coming out from the origin here. And the one side, hold on, come on, give me the line. The one side I keep as is. And then I just draw, for the other side, I draw the general vector AB. And those two sides define this parallelogram. Now the question is, geometrically, I want to be a little careful here. I want to see if even I need to do this. I think I do, though. Yeah, I think I do. So the area here, the area of this parallelogram, well, what would the area equal? Well, what I can do is I can go back to my rectangle idea. Okay, I can make this rectangle here. Okay, I can make this rectangle here. And the rectangle had, hold on here. This rectangle has the height. Well, what's the height of that? I'm sorry, what's the height? I'm sorry, this triangle here, this triangle, I'm wondering what the height is of the triangle. Okay, the height is B. Okay. And for this triangle here, what's the base for that triangle over there to the left? It's probably easier to A. So you have a triangle here that has base A and height B, and I want to be a little bit careful here. Are we in agreement that both triangles are the same triangle? In other words, the areas of both those little triangles, or both those triangles, are they the same? Do you agree that they would have to be the same triangle? Okay, they'd be the same. All right, what's the area of the entire rectangle? Well, okay, hold on. Hold on. The area of this triangle here is 1/2 A times B, right? 1/2 base times height. And the area of this triangle is 1/2 base times height. So then what's this area have to equal here in the middle of the parallelogram? It has to equal, good, Haley, A times B. Good enough, funny, A times B. Because the entire rectangle that I've drawn here the area is rectangle area has to be what? What's the area of the rectangle? That's right, Nafani, 2 times A times B. 2 times A times B. So if you take 2 times A times B and subtract off 1/2 A times B, the area of that triangle, and subtract the area of the other triangle as well, 1/2 A times B, you get the area of the parallelogram that remains, and that would have to be A times B, because 2 times AB minus 1/2 AB minus 1/2 AB gives you A times B. How many think that's a pretty cool geometric representation there? Okay, thank you, Haley. Maybe it'll look good in the recording if maybe another person says yes too. But now I don't know if it counts, because see, Haley did it on her own free volition. But how many think this geometric proof of the area of that parallelogram equaling AB is kind of interesting, at least interesting? Okay, thank you, Eleanor. I appreciate that. Thank you, Abby. Thank you, Lewis, Hung, Naima. I appreciate it. Very good. So okay. Thank you, Shravani. And so we agree that the area of that parallelogram is the same as the area of that rectangle when we define the parallelogram, the sides of the parallelogram to be the vector A over B and the vector A over 0. So now let's look at the determinant of a matrix A whose columns are AB and A0. Let's go to the next page here. Here's a matrix A, okay, whose column vectors are A0 and AB, which are the vectors that define the sides of the parallelogram. Well, if you take, I'm going to say this the right way. And on the right hand side, I have a matrix A whose columns are the sides of the rectangle that you saw. Well, if you take negative A over B times, now hold on here. Hold on, I want to say this the right way. One moment, class, one moment. Yeah, if you, actually, hold on. Yeah. This row operation, if you do it to actually this matrix here, if you take the second row and multiply it by negative A over B, okay, and add that to the first row, then the row equivalent matrix is going to be this matrix. So the determinants are the same because this here is just a row replacement operation. So the determinant of this matrix equals the determinant of this matrix. And that's true. But we also know that this determinant here represents the area of the parallelogram, and this determinant here represents the area of the rectangle. But the point is that the determinant then of since this equals A over B, that establishes that the area of the parallelogram determined by these columns here is equal to the absolute value of the determinant of A. Okay, does that make reasonable sense? It takes a little time to think it through, but hopefully, I mean, this is I just wanted to give you a little appreciation of that theorem, and not just sort of. I just wanted to give you a little intuitive feel for the theorem. So now our time is up, but I have one quick favor to ask you. Can you just check? So I'm going to have some. I got to post. You've worked on a few assignments. On Monday, on Monday I will have assignments ready for. What I'm trying to say is the assignments that are due on Monday are going to be the 3.2 multiple choice exercises, along with exercises from 3.3. 3.3, the free response, I've made that available now, and I just wanted you to maybe just open that up for a moment, just for a quick moment. And it's not a huge assignment, but I just wanted you to peek at it real quick, and I think you'll find the problems interesting. Is 3.3 showing in the My Math Lab? Is it visible there? The 3.3 free response exercises. Okay, good. All right. So what I'll do is after class, I'll activate all the assignments. The assignments that are due on Friday, they will be ready like right away for you to work on. And then the ones that are due on Monday, I'll need a little more time to get those ready. But this is one of them, the 3.3 free response exercises. All right, let me stop the recording.